Okay, now on this slide we have a little bit of a reiteration of the example of the 1 and 2 Coke cans that I gave you earlier in the semester. And the title just indicates something that you already know, that the Gibbs free energy depends on temperature and pressure. And we've already seen how it depends on temperature, and we'll see in a little bit how it depends on pressure. But before we continue on to that, I just want to reiterate the example of the 2 Coke cans and the difference between extensive and intensive variables. So in the first case, I have you consider the system to be one single Coke can, and it has a certain Gibbs free energy, and it's equal to the Gibbs free energy of a single can of Coke. And then in the second case, I have a system consisting of 2 Coke cans, and in that case, the Gibbs free energy of that system of 2 Coke cans equals 2 times the Gibbs free energy of 1 Coke can. So this just shows how the Gibbs free energy is extensive. So delta G extensive, because it doubles when we doubled the size of the system by including 2 Coke cans here. Now in contrast, mu, because it equals the molar Gibbs free energy, it does not double by doubling the number of Coke cans, because it's the Gibbs free energy per mole. And so the Gibbs free energy per mole does not change depending on the size of the system. So these are intensive. And that's why in this chapter we're using these molar thermodynamic quantities and not the extensive thermodynamic quantities. Okay, before we get to the pressure dependence of the Gibbs free energy, I want to return to a similar plot to what we saw last time. If on this axis we have temperature, this axis we have the molar Gibbs free energy, or we could say the chemical potential, mu. What if we rearrange these lines in a slightly different way than we saw? So there's our delta Gm of the liquid, and here we've got our delta Gm of solid. And now we've got our delta Gm of gas. How is this different from the plot that we saw in the last video? It's different because at no point is the liquid phase the lowest in terms of Gibbs free energy. So this is interesting. What does this mean? This means that we have a point here where the transition goes straight from the solid phase to the gas phase. And that corresponds to the sublimation point. So this plot represents a phase transition that you might see for CO2 at standard pressure. The transition from dry ice, say, over to CO2 gas, like so. Now let's consider one more possibility with regards to temperature change, delta Gm, or chemical potential mu. We've got our liquid line again. And then we've got our solid line here. And then our gas. And they all cross at exactly the same point. What is that right there? It's a temperature where the solid, the liquid, and the gas are all simultaneously possible. And hopefully you recognize that that is the triple point of the pressure temperature phase diagram. So what about pressure, you ask? We're going to be constructing some other curves that are very similar to what we saw with temperature in order to find the molar Gibbs free energy. And in order to get those, we need to remember our formula for the enthalpy. The molar enthalpy is going to be equal to the molar internal energy plus molar volume times change in pressure. So since the molar Gibbs free energy is equal to the molar enthalpy minus the molar entropy times temperature, I can just rewrite this as molar internal energy minus the molar entropy times temperature plus molar volume delta P. But this right here, that is just the molar Helmholtz. Right, so the way that the Gibbs free energy changes with pressure is that the Helmholtz tells us where the intercept is going to be, kind of like how enthalpy was with the temperature plots. And the slope is going to depend on the molar volume times the change in pressure. Okay, so now we're going to run into a number of different possible substances. Most commonly, the molar volume of the solid is going to be less than the molar volume of the liquid, which is going to be less than the molar volume of the gas. This is most substances. You probably all know about the most important exception to this rule. H2O. Water is the most important exception to this, but for most substances, this is true. So let's go ahead and plot, similarly to how we did before, the pressure against the molar Gibbs free energy. What are we going to get? We're going to have the largest molar volume for the gas, so that's going to result in a line that is very steep, like so. And then the liquid state is going to have a smaller slope like this, and then the solid state is going to have the lowest slope like that. So here's gas, liquid, solid. So that means that as the pressure goes up, we're going to be going from the gas state, then when the pressure gets high enough, we'll have a transition to the liquid state, and then a transition to the solid state like that as the pressure goes up. And of course, another possibility is that the curves don't line up in exactly the same way. So we'll have the gas, and then we'll have the liquid, and then we'll have the solid. And in that case, we'll have a transition straight from the gas to the solid with an increase in pressure. That is also possible. Then if we have all three of those curves intersect at exactly the same point, that corresponds to the triple point. Now, of course, for the situation where we have Vm liquid is the smallest, followed by solid, followed by gas, then we're going to have a different curve. Pressure down here, Gm or mu. Gas is going to have the largest slope, followed by solid, followed by liquid. Down there. So then we'll have a transition from the gas state to the solid state to the liquid state. This is the case for H2O and a limited number of other substances besides H2O. This means that with compression, solid water or ice will convert to liquid water even if the temperature is below freezing with high enough pressure. So now on this slide, we actually have a picture of a pressure temperature phase diagram, which depicts exactly what we've seen on the last few slides, but it doesn't have the Gibbs free energy explicitly plotted. It just shows the phase that the system is going to occupy. So the last slide that we saw was an increase from zero pressure up to a higher pressure. So that would be like the system going from the gas state to the liquid state to the solid. So this is a phase diagram for water, most likely. And so that's an increasing pressure sort of a situation. Then a few slides before that, we saw a phase change from low temperatures, which went to the solid phase, then through the liquid phase, then to the gas phase like that. And we'll see how extremes of pressures and temperatures will result in some interesting, strange situations with regards to phase in a few slides. So now on this slide, we begin to think about how changes in pressure can change also the temperature at which phase transitions occur. And so in cases where we're increasing the pressure, we're actually going to be increasing the boiling point as well. And that's called a boiling point elevation. And we can explain this by thinking about the previous slides where we looked at how pressure changes will change the Gibbs free energy in relation to how big its molar volume is. So if we consider a small change in the enthalpy, molar enthalpy, this is going to be equal to the molar volume times the change in pressure. And so since the molar volume of a gas is always going to be a lot larger than the molar volume of a liquid, we're going to have a much bigger change in the enthalpy as a result of the same change in pressure. Okay? And since the Gibbs free energy is proportional to the enthalpy, an increase in enthalpy is going to result in an increase in the Gibbs free energy. So now let's make a plot where down here we've got temperature, and over here we have the molar Gibbs free energy, or the chemical potential. Let's have a curve here that represents the liquid, and then we can have a curve here that represents the gas. Now let's take the situation where we have an increase in pressure. So we'll call this situation low pressure. Then we have a slight increase in pressure, and I'm going to use a different color here. We're going to shift the Gibbs free energy slightly by going to a high pressure. But the shift is going to be quite a bit larger for the gas than it's going to be for the liquid. See how the liquid curve is a lot closer to what it was previously with that change in pressure. So what effect is that going to have? That means that at the low pressure, we're going to have a different boiling point than we had for the high pressure. See? So we had an increase in the boiling point, and that's called a boiling point elevation. So yes, increasing the pressure is going to increase the boiling point for the exact same reason that this combination of pressure and temperature change is changing the Gibbs free energy. Next, we're going to consider liquid to solid transitions. And let's first consider the situation where the molar volume of the solid is less than the molar volume of the liquid. This is the case for most substances besides water. So down here we have temperature, and over here we have delta Gm. And we've got the curve for the liquid. And up here, we've got the curve for the solid. This is our low pressure color, And then we've got a color representing the high pressure as well. Remember, we're going to have a more pronounced change for whichever phase has the bigger molar volume. So that means that our jump in Gibbs free energy from raising the pressure is larger for the liquid than it is for the solid. So that means that at low pressures, we're going to have a lower freezing point in terms of temperature, and we're going to have a higher freezing point for that higher pressure. So this is a freezing point elevation because right here we've got a change in that freezing point. In comparison, let's consider the situation where the liquid molar volume is smaller than the solid molar volume. As before, we've got temperature on this axis, molar Gibbs free energy on this axis. And because we're not changing the entropy, the slopes of these two are not going to be any different than they were before. So this one with the larger slope is still the liquid, and this one with the gentler slope is the solid. But now, when we go from low pressure to high pressure, the solid is going to jump up more than the liquid is going to. So as you can see, the freezing point has actually decreased with an increase in pressure. And this is called a freezing point depression. So for substances like water, increasing the pressure is going to decrease or depress the freezing point.